Alright, so in the previous video I shared with you a formula that you can use to write the general solution when you have complex eigenvalues and complex eigenvectors in your system of differential equations, right? Now, where do I get that formula? How to derive that formula? So here's the explanation. Now, when you have a system where you have complex eigenvalues, now it's not a secret that you only work with the one eigenvalue, naming alpha plus I beta, and we know the other eigenvalue is complex conjugate, alpha minus I beta. Let's call it lambda 1 bar. So bar means the conjugate, and we know the eigenvector for lambda 1 is k1 and its complex conjugate is k1 bar. Let's say that it's k1 bar really, but we don't use lambda 1 bar and k1 bar. It seems to be like we were not using in the last video, right? But really we do use them. Here's what happens. So we know lambda 1 k1, we know lambda 1 k1 bar. So what are the really solutions of the differential equation, assuming it's 2 by 2? When the two solutions are k1 e to the lambda 1 t and k2 e to the not k2, my bad, k1 bar e to the lambda 1 bar t, right? So that this is the assumption that we made in the very beginning of the section, right? Our solution should look like eigenvector times e to the eigenvalue, corresponding eigenvalue, right? So going based on that theory, well, these are the two solutions, right? Now then you can take the linear combination of them and can we write the solution? Here's the thing, we know two solutions. So this 1 is a solution, 2 is a solution. If you want another solution, what can you do? Well, we can use the superposition principle. So superposition principle means if you add both of these solutions, that will be also a solution. If you subtract these two, that is also will be a solution. And let's say you multiply the first solution by 3 and multiply the second solution by 5 and then add both of them, that's also a solution. That means constant multiple plus or any linear combination of 1 and 2 is also a solution. Okay, so based on that, I'm going to construct two solutions, two linearly independent solutions, because for a fundamental set of solutions you need linearly independent solutions, right? That is something that you often forget. So I am going to construct my x1 as half times, well, it's a constant, okay, k1 e to the lambda 1 t plus k1 bar e to the lambda 1 bar t. So I just took these two solutions, add them and divide by 2. Okay, that's what I did. And I construct my x2 as I over 2, that's a constant, minus k1 e to the lambda 1 t plus k1 bar e to the lambda 1 bar t. So what I did here to construct the second solution is I subtract equation 1 and 2 and multiply it by I and divide by 2. So that is how I create my two linearly independent solutions. Okay, alright, so now we have x1 and 2. Now you will see there's a major difference in what I show you in the last video and this video, right? Last video I had like sine beta, cosine beta, and how did I get them? Here's how I got them. So we have this famous identity which is really an analog for section 4.3. okay, remember when we have complex roots we wrote our solution with sine and cosine, right? Cosine beta t, sine beta t, same thing happens. Okay, we have this famous formula, e to the I beta t can be written as cosine beta t plus I sine beta t. Now if you have the negative I beta t exponent, you have cosine beta t minus I sine beta c. So this is an identity, right? Okay, so we can use these two identities. How? So let me show you this for just a x1. Okay, so x1 is half. Now what I'm going to do is k1, lambda 1 is alpha plus beta I, right? So let's write alpha plus beta I t. So I replace lambda 1 here by its real identity, alpha plus beta I, right? Now you have a plus in the exponent. So we can use product rule, right? So e to the alpha plus beta it can be written as e to the alpha t, e to the I beta t, right? You distribute the t and you break them up from the top, right? So instead of writing this one, we can write e to the alpha t, e to the I beta t. Here then k1 bar. Okay, now you have lambda 1 bar, so that means e to the alpha minus I beta times t, right? So this can be breaked up as e to the alpha t, e to the negative I beta t. Okay, so that is what we can do. All right, so now what I'm going to do is, as you can see here, there's something common. E to the alpha t is common, so let's take it out, e to the alpha t. So we get k1 e to the I beta t plus k1 bar e to the negative I beta t. Okay, so that is what we get for x1. Now, you know e to the I beta t is really cosine beta t plus I sine beta t. So let's quickly write it down. Half e to the alpha t, here k1. So let's distribute the k1 in the process. K1 cosine beta t plus I k1 sine beta t. Now here k1 bar plus e to the negative I beta t is really e to the negative I beta t is really cosine beta t minus I sine beta t. So we can write k1 bar cosine beta t minus k1 bar sine beta t. Okay, k1 I sine beta t. Okay, all right. So now we have this. Let's group the terms. Group the terms means we have cosine beta terms. So let's group the cosine beta terms together. So half e to the alpha t. So we can take out a cosine beta t. So it's k1 plus k1 bar cosine beta t. So let's group the sine beta terms together. Let's have a minus. Let's factor a minus I also, because I is also common. So we get minus k1 plus k1 bar sine beta t. So I factored a sine beta t and a minus I. So this is what I get for x1. Okay, so let's go back to the note. So it was a little bit long. So let's go back to the note. So I showed you this is what I got. I proved you how I got that this long x1, right? So if I do the same for this x2, that means write lambda 1 as alpha plus beta I and lambda 1 bar as alpha minus I beta, and then use this two identities. This is what I get. Now here's one thing that I want to focus. Now you might still say, well, wait a minute, this is still very different from what we used in the last video. Look at these interesting terms. So I'm gonna circle this half k1 bar, half k1 bar here. So see, these two are same, and I'm gonna circle negative, not negative, I over 2 negative k1, this term and this term. So you can see these two terms, these same color terms are similar, right? Same terms. Now let's focus on the red term, because that red term is very special. Even the green term is also special, but if you understand the red term, you can understand the green term too. So red term say k1 plus k1 bar over 2. So that is what I got when I simplify here, right? So that is what I got when I simplify here. See, k1 plus k1 bar over 2. So they have just distributed the half in the note. Okay, all right. I want to give just a justification. So now what is k1 plus k1 bar? Let's look at something simple. So k1 plus k1 bar means you add the complex conjugate to yourself and divide by 2. Right? K1 is the original complex vector. You add its complex conjugate and you divide by 2. So let's look at the complex number version of this. You have alpha plus beta I and you add your complex conjugate to it, alpha minus beta I. So what you get is beta I cancel out, you get 2 alpha. Now you divide this by 2. So 2 alpha divided by 2 is alpha. Now what is alpha? Alpha is the real part of the complex number. So guess what you get here? The real part of the complex eigenvector. That's the analog for vectors. Okay, so B1 is K1 plus K1 bar over 2. So similarly, so this red color part, the red color part is B1. Then what is the green color part? So I over 2 times negative K1. This can be exercise for you. This is actually the imaginary part, or the B2. If you do it, you will see it. Okay, so this green color term is the imaginary part, B2. So we can, that is how we get this solution. So now let's rewrite our x1 and x2 in terms of B and this sine and cosine term. So x1 is from here. This is B1. B1 e to the alpha t cosine beta t minus this is B2. B2 e to the alpha t sine beta t. Now what I can do here is I can take out e to the alpha t out, and this is exactly what we get. So that is how we get our formulas, and that is how we get our x2. Okay, so that is how we get our x1 and x2 formulas. So really we start with the simple hypothesis that we had in the beginning of the course, where the solution is eigenvector times e to the lambda t. Then we use the superposition principle and construct these two linearly independent vectors, and we use the Euler's identity. This identity here is called the Euler's identity, and we do a simplification, and we use these two facts and get these two results, which looks nicer than what we started with. Okay, so again, as I said, you should check with your instructor to know whether you have to memorize these formulas or these formulas will be given in the exam. But yeah, then you just take the linear combination of x1 and x2, you get to write the final solution, right? Okay, thank you very much then.